Hello math students. Today's video is lesson 3.5, scene structure. In today's lesson, we are going to actually start graphing polynomials. Up until this point, we've reviewed factoring, and then we've talked a lot about the end behavior of functions. We are going to actually use that information to graph an entire function. Polynomial functions have some interesting characteristics. Up until this point, we've really just been looking at degree and leading coefficient to tell us information about the end behavior, but the degree also tells us the number of roots. Just in case you don't know, a root is just another word for x-intercept. Or I should say a real root is an x-intercept. There are some slight differences between the two words, but for the purposes of our class, a root and an x-intercept are the same. Relating to a root, we have what's called the fundamental theorem of algebra. The fundamental theorem of algebra says that an nth degree polynomial has n roots. If you remember back in secondary math 2, we did a lot with quadratics. When I graph a quadratic, it gives me a parabola. I either have a parabola that gives me 2 real roots, a parabola that touches the x-axis, and as a result gives me 1 real root, or we had the case where it never even touched the axis. This, we would say, has 0 real roots, but I could say that it has 2 imaginary roots. So what we want to do is, once we look at polynomials with degree greater than 2, we want to see if this fundamental theorem of algebra is going to work for all polynomial functions. To start with, we are going to make a conjecture or an educated guess as to the shape of each function. And then it says use technology to sketch the graph below. So our fundamental theorem of algebra is relating the degree with the number of roots. So I'm going to start by identifying the degree. When we define degree in the past, we have said that it's the biggest exponent. However, that only works if I'm in an expanded or standard form. If I was to go and expand number 1 out, which is in factored form, these two x's multiplied together are going to give me my biggest exponent. Because there's 2 x's, I'm going to say my degree is 2. According to the fundamental theorem of algebra, I should have 2 roots. If I was to go on a graphing calculator, so whether it's a TI 83 or 84 graphing calculator, some other handheld calculator, or something like Desmos, I would see on my graph that I have these 2 x-intercepts, and my graph looks something like that. This graph, like we expected it to, has 2 real roots. I have one at x equals -1 and x equals 2. We see this when we look at the equation. If I was to set x plus 1 equals 0, it's going to give me a -1. If I set x minus 2 equals 0, it's going to give me a positive 2. Number 2 is very similar to number 1, except for there is this exponent of 2. That means that the x that I have in the x plus 1 is really 2 different x's that are multiplied together, and the x on the x minus 2 is just 1x. So my degree, I would say, is 3, which means that I think I should have 3 roots. Once again, if I was to go and graph this on a calculator, I have these 2 x-intercepts right here. And my graph goes something like this. One thing that you'll notice is this only ever crosses or is on the x-axis twice. I have x equals -1 and x equals 2 for my roots. But one thing that you'll notice is at -2, my graph doesn't actually cross through the x-axis, it just touches the x-axis. In the equation, I have that exponent of 2. This x equals -1 really is two separate solutions to this equation. So I can say here that this has what is called a multiplicity of 2. That just means that this root is actually 2 roots. If I wanted to define multiplicity, I could say that it is the number of times a root is the solution to f of x equals 0, or it also ends up being the exponent of the factor where we get the root from. Three and 4 are the same kind of thing. I want to identify the degree. On number 3, both factors have an exponent of 2. So this is really x plus 1 times x plus 1 times x minus 2 times x minus 2. So there's really 4 x's that are being multiplied together, so my degree is 4, which means I should have 4 roots. When I graph it on my graphing calculator, it ends up looking something like this. Once again, the number of x-intercepts is different than what we said the number of roots was going to be. My roots, I have one at x equals -2. Excuse me, x equals -1 and x equals 2. However, I could say that each of these roots have a multiplicity of 2. And a lot of times instead of writing the whole word at, I will go mult 2. We see that in the exponent. So there's an exponent of 2 on each factor. Or there are 2x plus 1s. So if I was to set this equal to 0 and solve for x, I would have x equals -1, x equals -1, x equals +2, and x equals +2. So each solution shows up twice. On number 4, my equation is just f of x equals x plus 1. My biggest exponent is a 1, which means I should have 1 root. This is one that we can hopefully graph without a graphing calculator. It's a line with a y-intercept of 1 and a slope of 1. So it goes something more or less like this, except for straighter. This has 1 root at x equals -1. And I'm going to go ahead and say that the multiplicity is 1. If the multiplicity is 1, you don't have to write it out. Similar to how if I have an exponent of 1 or if there's a 1 multiplied out front, you don't have to write the 1. Number 5 is very similar to number 4, except for I have an exponent of 2. So my degree is 2, which means my number of roots should be equal to 2. However, when I graph it, it goes something like this. I have a single x-intercept at x equals -1. Because my exponent is a 2, I'm going to say this has a multiplicity of 2. Number 6, same kind of thing, except for there's an exponent of 3 now. I'm going to say my degree here is 3, because if I was to multiply everything out, I end up with 3 x's multiplied together. The number of roots should also be 3. When I go and graph this one, it goes something like this. Once again, there is only one actual root at x equals -1. Because my exponent is a 3, I'm going to say I have a multiplicity of 3. One thing hopefully you noticed as we were looking at the different graphs is some of the graphs touched the x-axis at the root. Some of them crossed through. The thing that determines whether it's going to cross through or simply just touch is that multiplicity. If you have an even multiplicity, that means that my graph is going to just touch the x-axis, but not actually cross through. If I have an odd multiplicity, my graph crosses through the x-axis. For these last few examples, we're going to go and actually use this information to help us create a sketch of a graph without using any kind of graphing calculator. The 3 things that I'm interested in knowing are the x-intercepts, the y-intercept, and the end behavior. To find an x-intercept, all that you need to do is set f of x equal to 0. So instead of writing an f of x, I'm going to set the whole thing equal to 0. So I can say -x times x minus 2 times x minus 4 equals 0. That means that -x has to be equal to 0, x minus 2 has to be equal to 0, or x minus 4 has to be equal to 0. If I solve each of these equations, I get x equals 0, x equals 2, and x equals 4. Because my exponent on each of these factors was a 1, I could say on each of them the multiplicity is 1. To find the y-intercept, what you want to do is plug 0 in for x. So I'm really looking to see what is f of 0 equal to. Or replace all the x's with a 0. -0 times 0 minus 2 times 0 minus 4 is simply equal to 0. To find the end behavior, we need to know what is the degree, what is the leading coefficient. The degree is your biggest exponent when everything is multiplied out. On this one we have a 3, my leading coefficient is going to be a -1. Because the coefficient of each x is 1, if I multiply everything out, I have that -1 out front, which makes my leading coefficient -1. When we're doing end behavior, the leading coefficient tells me what happens on the right side of the graph. So I can say as x approaches positive infinity, f of x approaches negative infinity because my leading coefficient is negative. Because I have an odd degree, the left and right sides are opposite. So I'm going to say as x approaches negative infinity, f of x approaches positive infinity. This is really saying that my graph is going down on the right side of the graph and up on the left side of the graph. So let's go put what we know on the graph. I know that I have x-intercepts at 0, 2, and 4. I know I have a y-intercept at 0, which is the same as the x-intercept. And then I know as my graph is going to the right, it's going down. As I go to the left, it's going up. So I have to come from the top. Because all of these have a multiplicity of 1, I'm going to cross through the x-axis at the root. I have to go back up to my next x-intercept and then go down. And that is what my graph looks like. One little piece of information, I'm going to say the number of times a graph changes directions is 1 less than the degree. So at number 7, I can only change directions 2 times because my direction or my degree is equal to 3. However, I could change directions 1 or 2 times or 0 times. Number 8 is very similar, except for I need to factor this quadratic right here. So I'm looking to find 2 numbers that when I multiply them together equal 4, when I add them together equal 4 as well. The only number that works is 2. 2 times 2 equals 4. 2 plus 2 equals 4. So I'm going to rewrite this as x times x plus 2 times x plus 2. And I'm going to set this equal to 0. Or I could say x times x plus 2 squared equals 0. I'm going to set each of these factors equal to 0. I have x equals 0. That's as far as I can go. And my multiplicity on this one is a 1. I can also say x plus 2 equals 0. If I subtract 2 from both sides, that gives me x equals -2. Because my exponent was a 2, that means I have a multiplicity of 2. To find the y-intercept, I'm looking to see f of 0 equals 0 times 0 squared plus 4 times 0 plus 4 is just equal to 0. And the end behavior, I have an odd degree. I have a positive leading coefficient. So as my graph goes to the right, I'm going up. As I go to the left, I'm going down. When I go put this on my graph, I'm going to put my x-intercepts on. I've got one at 0, one at -2. My y-intercept is my x-intercept. As I go to the right, I'm going up, left, goes down. So I start from the bottom. Because -2 has a multiplicity of 2, I reach there, touch it, come back down, go back up. That is my graph. Same kind of thing on number 9. I need a factor. So what multiplies to give me a -2 adds to give me -1. So -2, sorry, yeah, -2 and +1. So I'm going to rewrite this as x minus 2 times x minus 2 times x plus 1 equals 0, or x minus 2 squared times x plus 2 equals 0. That gives me x-intercepts at x equals 2, which has a multiplicity of 2, and x equals -2, which has a multiplicity of 1. For the y-intercept, I'm going to replace the x with a 0. So I have 0 minus 2 times 0 squared minus 0 minus 2. When I multiply that all out, it gives me a 4. I have an odd degree with a positive leading coefficient. So it means as I go to the right, my graph goes up. As I go to the left, I go the opposite direction. So I go down. So I am going to put my x-intercepts on the graph. I have one at 2 and one at -1. As I go to the right, I go up, left goes down. So I come from the bottom, at -1, I have multiplicity. Sorry, I put that at -1. I meant to put it at +1 or -2. So at -2, I have a multiplicity of 1. So I'm going to cross through. I come up to my y-intercept at 4. I just realized I wrote this whole thing down wrong. This was supposed to be an x plus 1 right there. So my x-intercept is at -1. There we go. Now this is correct. So I've got -1, has a multiplicity of 2, come up to my y-intercept at 4, -2 has a multiplicity of 2. My graph looks something like that. I think I said -1 has a multiplicity of 2. I meant to say it has a multiplicity of 1. The last two are the same kind of thing, except for if I look at number 10, I have x cubed minus 9x. We haven't done a lot where there's an x cubed actually in my equation. But one thing we'll notice is both of these have an x. So I am going to factor out an x. So this is really x. If I take an x away, there's really x squared and 9. And then I can finish factoring this. To factor x squared minus 9, I'm going to see what multiplies to give me -9. Because I don't have that x term, I'm wanting to add it to a 0. The only numbers that work are 3 and -3. So I can factor this as x plus 3 times x minus 3. To find the x-intercepts, I'm going to set all my factors equal to 0. I'm going to say x equals 0, x plus 3 equals 0, x minus 3 equals 0. That gives me an x-intercept at x equals 0, which we already have. X equals -3, and x equals 3. Y-intercept is f of 0, which is 0 cubed minus 9 times 0 squared, which is just 0. End behavior, odd degree with positive leading coefficient. We've done a bunch of these already. Up to the right, down to the left. And go ahead and put this information on the graph. I have x-intercept at 0, -3, and +3. I'm going up to the right, down to the left, and all of these have a multiplicity of 1, so I'm just going to cross through. And that's what my graph looks like. Last one we're going to do is number 11, which is f of x equals x squared times x squared plus 3x minus 4. I still need to factor the second quadratic, so I'm looking for numbers that when I multiply, give me a -4. When I add them, give me a +3. The numbers that work for that are going to be a -1 and a 4. So I can rewrite this as x squared times x minus 1 times x plus 4. And then to find the x-intercept, set it equal to 0. So I have x squared is equal to 0, x minus 1 is equal to 0, and x plus 4 is equal to 0. If x squared equals 0, that means x is just equal to 0. But because I had the square, I'm going to write this as a multiplicity of 2. X minus 1 equals 0 means x equals 1. X plus 4 equals 0 gives me x equals -4. The y-intercept is just f of 0. So I have 0 squared times 0 squared plus 3 times 0 minus 4 is just 0. For the end behavior here, my degree is 4. My leading coefficient is a 1. So I have a positive leading coefficient. So as I go to the right, I'm going up. And then I have a even degree, which means the left and right sides are going the same direction, which is a little bit different than the ones we've been looking at so far. We've been looking at degree 3. Right now we're looking at degree 4, which means both sides go up. I'm going to put my x-intercepts on the graph. I have an x-intercept at 0, +1, and -4. So I have to come from the top. Because -4 has a multiplicity of 1, I cross through, come back to the 0, and then I am just going to touch at 0, go down real quick, and then come back up at 1. And that is what my graph looks like.